Hello, my name is Adam Rahman, and I'm delighted to present my submission for ArangoDB's 2025 Agentic App Hackathon, titled AskStreets, Querying and Visualizing Street Networks with OpenStreetMap, ArangoDB, and LangGraph. To introduce myself, hi again, I'm Adam, Wesleyan class of 2019, former intern at UNICEF Innovation in New York City in 2018, and I'm currently a mainframe developer at IBM. I enjoy tinkering with new tech, and I knew this hackathon would be a great opportunity to not only build upon past work, but also create an exciting new project with AI. Speaking of past work, it was my internship project at UNICEF that really inspired me to participate in this hackathon. At UNICEF, we sought to generate insights with large data sets from UNICEF program countries to address a critical real-world issue. Given lists of schools with corresponding geospatial points and a database of health facilities, how far is each school from the nearest health site, taking into account the road or street infrastructure of where that school is located, and what are the ramifications of this data on healthcare accessibility? The solution was to create a correspondence between national road networks and graph data structures. I used the OSM-NX, that is, OpenStreetMap Network X, Python library to build these graph networks, and used NetworkX and iGraph code to compute the necessary algorithms to build datasets and then visualize them in Kepler-GL. This data would also be handed off to UNICEF data scientists for further analysis. The code is available on GitHub, and I've blogged about my process as well. Here is some sample code from that project, demonstrating routed distance calculation for a school and a health site, as well as a visualization using the generated distances dataset overlaid with population, allowing one to discuss correlations such as between population density and healthcare access. This project offered a lot of value, both to the company and to myself. And with my experience with NetworkX, I wanted to build upon this and generalize the challenge to a broader context for this hackathon. To present the current business case, assuming the role of someone with a vested interest in street networks, whether you're a city planner, business owner, researcher, or architect, you'd like to be able to gain insight into the properties of a street network without needing extensive coding or data skills. You may wish to understand street connectivity, how reachable certain areas are, landmark clustering, and accessibility of services, which can help in the process of establishing where to construct new businesses, build new bike paths or shelters, which health facilities to allocate resources to, and so on. My solution is AskStreets, an agentic AI app that can translate plain language and deploy powerful tools to generate meaningful insights into street networks. Backed by comprehensive and up-to-date data, this AI app can identify locations from a query, find relationships between certain geographic features and the properties of a street network, execute algorithms to report on network attributes like centrality, and also create an immediate visualization of relevant points to aid in analysis. Such a tool would empower the user to ask meaningful questions about a street network in a real-world context. A quick overview of the dataset that we're running our queries against. OpenStreetMap is an open-source and community-driven map and database. We chose to use it with our UNICEF project due to its global reach and emphasis on local knowledge, improving data quality. And for that same reason, I'll be using it in AskStreets. Its open nature means it's up-to-date, which will improve the accuracy of answering queries. And crucial to our needs, it has a rich ecosystem, an API with a well-established schema, and libraries like OSM-NX, which will do the heavy lifting of converting OpenStreetMap data to NetworkX graphs and Pandas data frames, allowing us to run code on it and then generate the insights from our map data that we want. We'll now be moving on to the demo portion to witness AskStreets in action. Here is the Jupyter notebook for AskStreets. We start with our necessary Python imports, as well as environment variable setup for GPU acceleration. We then confirm the NVIDIA CUDA toolkit is available and that there is a GPU for us to use. The correct variables are also set to enable NetworkX GPU acceleration. The first major step is preparing OpenStreetMap data to load into ArangoDB. First, we build the graph network from OpenStreetMap using OSM-NX's built-in graph from address function. In this case, I'm using my workplace of IBM 1 Madison Avenue as our center point and create a graph with a 250-meter radius. We then visualize the graph and can see how the nodes and edges correspond to real-life intersections and paths. For more rich data, we reverse geocode each node of the graph with OpenStreetMap's nominatum geolocator. We set an ID field for each node that corresponds to the network X ID. That way, later on, Python code can hand off node information to ArangoDB query language, and it can filter on this attribute. To save time in retrieving OSM data in the future, we save the graph to disk as a GraphML file. This can also aid in future projects that would be able to read this file type. Here's some sample node and edge data, where you can view attributes like latitude and longitude, how many streets are connected to a node, addresses, length of pathways, and so on. To enhance the database our tool can run queries against, we'll also collect OSM features and load them to ArangoDB as a collection. We'll retrieve the features from the same location bounding box and specify tags such as what type of amenity each feature is to enrich our data. We process the data to make it easier to serialize for ArangoDB and present some sample features. We are now prepared to load our OpenStreetMap data into ArangoDB. Let's go ahead and load in the credentials from a YAML file, set them to variables, and connect to the ArangoDB client. We'll be creating a new bit database to store our Madison Avenue information. We then persist the data to a multi-directed graph to ArangoDB and make sure we have the right number of nodes and edges. Then, we load in our OSM features as a collection to this database. And finally, to end this step, we'll initialize the LangChain wrapper for ArangoGraph to use the specific Madison Avenue database, and we're all set with preparing the data for the agentic app. Moving on to the tools. We'll have 4 of them for LangGraph's React agent to answer queries if. A text to ArangoDB query language translator, a text to OSMNX Python code translator, a geocoder, and a visualization tool. Some quick setup work. We'll define the AI platform of choice and then load in the respective API key. This simplifies the process of switching LLMs for all the tools to use. Starting with the text to AQL translator. We define the docstring as its tool description, initialize the LLM, then build context to enrich the query for the ArangoGraph query chain. This enhanced query will now include more information from the database schema, including the node, edge, and feature attributes. There's also more detail about how to approach specific queries. This context is prepended to the user query and is passed into the chain, which will then return the analysis. Next is the text to OSMNX and NetworkX translator. I find this portion particularly exciting. As someone who has written OSMNX code 7 years ago, it's fun to build a wrapper that can generate specific code to solve a problem. We have our docstring and LLM loading as usual, and then an in-depth code generation prompt that guides the AI agent. The tool will generate and execute the code on the fly, and if it fails, there is a code correction mechanism built in. Once code successfully runs, the tool is instructed to generate a plain language explanation for the user. The next 2 tools are more straightforward. The geocoder tool invokes an LLM to extract location names from a query, then calls the nominatum geolocator to identify these locations in OpenStreetMap. If there's more than one possible location, it will attempt to narrow it down, and finally return the latitude and longitude of the primary location. And finally, the visualization tool will extract and clean up geospatial coordinates given to it by the query, and build a Folium map to load these points into. Then, displays the map immediately in the notebook. That covers our tools. Now, for the agentic app itself. To maintain our pattern of enriching our queries as much as possible, we keep a cache of tool results that subsequent tools can reference when building their queries. For example, in a hybrid query that generates AQL and then Python code, the query that is passed to the OSMNX tool can gain context by using the previous results. In this code, we wrap these tools with the ability to invoke themselves with enhanced context, referred to here as memory tools, and then pass them into the React agent. We update the system message context to reference previous results, then return the result of the agentic app as Markdown in our notebook. Now that both the database and the agentic app are prepared, we're all set to run queries against our graph network. Let's start with our first query. Which intersection in the street network is the best place to set up a new corner store, and what's the closest bank? Go ahead and run this cell. OSMNX interprets the query and generates the code. We'll then execute the code that's identified the most central intersection. The agent tries to use the geocoder but realizes AQL is better for solving this problem. The AQL chain is executed and the closest bank is identified. And finally, it returns the response. The best intersection is located at these coordinates. The closest bank is Credit Suisse, located at these coordinates. And we have the answer to this first query. The next query, visualize the top 3 most difficult to reach healthcare facilities in the street network. Let's run the cell. AQL interprets this query. And it identifies the top 3 most difficult to reach facilities. Passes it to the visualization tool. And let's adjust our Jupyter notebook in order to view the visualization. Zoom in on the map. And here we can see the top 3 most difficult to reach facilities have been plotted on the street network. Finally, what is the nearest bike shelter to 1 Madison Avenue, and how many meters does it take to walk there via a pathway? Let's run this cell. Geocoder identifies the coordinate for us, and then AQL finds the nearest bike shelter. And then OSMNX is going to calculate the shortest path and return the walking distance in meters. And we have our answer. The nearest bike shelter is at these coordinates. The walking distance is approximately 450 meters, or about a 5 to 6 minute block. We successfully ran queries against the street network of Madison Avenue. Next, let's use AskStreets with a rural street network. I've selected my father's village of Gomnati in Bangladesh for this example. We built a graph from a single point and a 3,500 meter radius. And we can see right away after plotting this graph that its attributes are noticeably different from that graph of Madison Avenue. We can see how nodes are more isolated from one another and edges have more varying path lengths, which will definitely have an impact on map traversal when we run our algorithms. As usual, we'll continue to modify this graph to make it easier to serialize for ArangoDB by geolocating all the points, adding the ID attribute. We display some sample node and edge data, and download the features dataset. But in this example, we're going to take advantage of another open source dataset from healthsites.io. This was one of the datasets I used for my project at UNICEF. They have per country datasets that can be retrieved via their API or downloadable as geospatial files. And in this instance, I have already downloaded the Bangladesh health site shapefile and loaded it into a data frame. We adjust this data frame and serialize it into JSON to pass into ArangoDB. With this health sites dataset loaded as a collection, we can also perform more enhanced AQL queries. We go ahead and we create our Gomnati database, load in the graph, add our features and our health sites as collections to ArangoDB, and initialize the database. And now we can run this query. What is the shortest path to the nearest health facility at this college? Let's go ahead and run the cell. The geocoder has identified the college location. AQL will find the nearest health sites by querying the health sites database that we just loaded in. And finally, OSMNX will calculate the shortest path. And it returns our answer. We've identified the shortest path between the college and health facility as 5 kilometers away within the street network. Recall earlier in our slides how at UNICEF I answered questions very similar to these, but I had to write Python code. Now, with this proof of concept, I've demonstrated that we can create an agentic AI app that will take these same natural language queries, generate the code for you, query the database, and run these algorithms. Now, there's definitely room for improvement here. We can update the tools to be even more precise, swapping in different models for different use cases, depending on what the tool needs to accomplish. We can also further update the visualization tool to illustrate shortest paths or demonstrate more attributes at those points. Thank you so much for watching my submission video. This was a really fun project to work on, and I'm also looking forward to browsing the project gallery and exploring all the other submissions to see what other kinds of problems other developers have been working on. I hope you have a wonderful day. This is Adam Rahman, signing off.